Hi, and welcome to lesson 20. Today, we're going to talk about degeneracy, convergence, and multiple optimal solutions. Up until this point, we've been talking about the simplex method. This week, you've run the full simplex method. We have not addressed two key questions. And the first question is, does the simplex method always stop? And then the second question, which we'll talk about on Monday, can we always begin? In other words, can we always find an initial basic feasible solution? However, today we're going to focus on the question one. And that's really connected to this term convergence. So just recall our stopping condition is when we have no improving simplex directions. Okay. As a warm-up, let's just talk about the simplex method on the following example. It's a max problem, similar to the ones we've been looking at. This is really similar to 8.1, I guess, because we have the three equality constraints with slack variables. And you can see that we have a basic feasible solution given here, 04030, with the following basis, y, s1, s2. And then the simplex directions, which are given, right, we have three variables that are basic, 5 total variables. So we then therefore have 2 simplex directions. And we want to compute x of t plus 1 and xb of t plus 1. So we've really started in the middle of an iteration. We, of course, have to compute our reduced cost for cx. Remember, that's just going to be the gradient of the objective times the direction of x, the dot product. When I say times, is what I mean, which is going to be equal to 10 times 1 plus 3 times 0 plus 0 times negative 1 plus 0 times negative 5 plus 0. And of course, this equals just 10. And c bar of S3 equals the gradient of f transpose d s1. And this equals 10 times 0 plus 3 times negative 1 plus 0 times 1 plus 0 times 2 plus 0 times 1. And that equals negative 3. Okay, so because we're maximizing, we have to choose Cx. And now we have to compute. So this was reduced costs. The conclusion from the reduced cost calculation is that dx is improving. Okay, so we want to now do the lambda calculation, so the step size. We are going to be able to do that from saying, well, xt plus lambda dx, as that's our improving direction, has to be greater or equal to 0. This is the same way as saying that, let's see, it's 0 plus lambda times d, which is 1, has to be greater or equal to 0. So that's not even going to be in a factor. It'll have 4 plus lambda times 0, greater or equal to 0, so that's not going to be a factor. It's going to have 0 plus lambda times negative 1 is greater or equal to 0. So that's going to be an issue because of the negative 1 there. And then we'll have 3 plus lambda times -5 has to be greater or equal to 0. And finally, we'll have 0 plus lambda times 0 is greater or equal to 0. And of course, this leads us to conclude that lambda has to be less than or equal to 0, or lambda is less than or equal to 3/5. So of course the winner, so to speak, is that fellow, and lambda max equals 0. Note that the min ratio test would have given us the same thing, because we would have said lambda max equals the min of 0 divided by minus 1 and 3 divided by minus 5. Okay, so these two methods, these are equivalent. However, the weird thing, because this equals 0, the weird thing here, of course, is that our lambda max is 0. So that means that xt plus 1 was just equal to xt plus 0 times dx, which is just xt. So the point did not change, but what happened? So we entered x, that's our entering variable. And our leaving variable, because that was this dx, our leaving variable, well, that comes from the candidate that gives us the minimum lambda we can choose for lambda max, right? So that's the most we can leave. And well, what variable was that? That was S1. So our basis, bt plus 1, now equals x, y, and S2. So this is true. Remember that bt equaled y, S1, S2. So our basis changed, but our point did not change. So we didn't have any geometric movement because the step size was 0, but we did have a combinatorial change. This gets at the point that we have to worry about, which is, do we ever finish? Now, the thing that we just observed was a result of something called degeneracy. Degeneracy means, for a basic feasible solution, the definition is that there are more than n constraints active at x. Recall that definition. The definition of basic solution had two parts. The first part was all equality constraints are satisfied. And the second part was at least n constraints active and linearly independent. Note the use of the word at least. We're very careful to say at least there. Now, I will note that because we're in an n-dimensional space, exactly most n constraints can be linearly independent. So this is at most. However, you can have more than n constraints active. Remember what active means? Satisfied with equality. Now, in this previous example, we did indeed have a degenerate point for xt. Why? Well, let's see. Remember, xt, I forgot what it was myself. What is xt? xt is 04030. Let's count how many active constraints there are. So the equality constraints are satisfied. There are 3 of them. So that means 3 active constraints. Remember, satisfied equality constraints are the same as an active constraint. And then the non-negativity. Well, we just have to count the number of zeros. There are 3 zeros, right? So that contributes 3 active constraints. So the total here is 6 active. But n equals 5. So yes, this is degenerate. In particular, for canonical form, we're going to have too many basic variables. All the equality constraints are always going to be active. So our degeneracy, our source of degeneracy in canonical form is always going to come from the non-negativity. We're going to have too many zeros. So a basic feasible solution, it has m basic variables, potentially non-zero. That's the key point here. And then it has n minus m non-basic variables always equal to 0 because these are equivalent to active non-negativities. So again, it's this issue, the potentially non-zero. This is what leads to degeneracy. So if it's a degenerate basic feasible solution with n plus k active constraints for k greater or equal to 1, then what that means is there has to be n plus k minus m non-negativity bounds that must be active, which is larger than n minus m. In other words, all k additional active constraints come from the non-negativity bounds, which means that a basic feasible solution of a canonical form LP is degenerate if there are n minus m plus k components equal to 0, with k greater or equal to 1. So what this also means is that you have a choice of bases. You saw this in that problem on the homework where you were given and there were too many zeros. And so you have this issue where you can have one solution that actually corresponds to several different bases. And then that's where we had to do the checks because perhaps not all of those bases are corresponding to basic solutions because you might not have linear independence. So there's that issue too. But they do have potential bases. And in particular for this one, the bases you can choose, you always have to have this y variable and the S2 be basic because they are non-zero. But then you have to choose one of x, S1, and S3 to be basic too, to form your 3 basic variables. So your 3 bases here are x, y, S2, y, S1, S2, and y, let me draw that a little neater, y, S2, and S3. So one basic solution, one basic feasible solution, one point in space with 3 potential bases. So in each step of the simplex method, we don't necessarily move to a geometrically adjacent extreme point, but you always move to an adjacent basic feasible solution combinatorially. You always move to a new basis. So the problem here is at this degenerate BFS, you might get stuck. And for a few steps, how big is a few? That gets a frowny face. So you know this happens when you get these 0 length moves. The lambda max is equal to 0. Note that this occurs if degeneracy is there, which means a basic variable is 0. A lot of times it's going to escape. I will note that degeneracy is the root of difficulty for many hard to solve LPs. And usually it occurs because there's a lot of structure in the problem. If you're interested in such a thing, I can talk to you about research ideas there and what people have been doing. I actually have done some work in that myself. It's a fascinating issue. Anyway, let's get back to a more fundamental one. We can, if we're really unlucky, get to a place where degeneracy causes the simplex method to cycle over the same extreme point. And you can see an example later, page 291, where you're using one pivot rule, say the densest largest cost rule, and it never leaves the extreme point, which means that you would not have convergence. So this is really bad. No convergence. So how do we guarantee that we actually terminate? We're going to use something called an anti-cycling rule. And it's called, the one that we teach you is called Bland's rule. It was one of the first ones developed. And what we do is we fix an ordering. So in this previous form, we would relabel the xy, s1, s2, s3 to x1, x2, x3, x4, x5. If you have entering variables, you choose the non-basic variable with the smallest index corresponding to an improving direction. So it has to be the smallest index. So if there's any ties, you always choose the one with the smallest index. And for the leaving variable, if there are any ties, you always choose the one with the smallest index. Turns out, and I'm just going to state the theorem, that Bland's rule prevents cycling in the simplex method. I'm just going to state it. The proof of this is actually one of the deepest proofs in fundamental linear programming theory. If you want to find out about the proof, you can ask me. I can also refer you to a textbook by Bert Seamus and Tsitsiklis. And if you want the exact reference, please ask me. It's Tsitsiklis. He has a Greek name. And we also have a homework problem on this, which I will post the solution for on Blackboard. And once I sign up, you'll see what the homework is. And it shows you an example of a cycling and how you can get out of it using Bland's rule. Okay. So that answers the question of convergence and degeneracy. I'm going to end this lecture by talking about multiple optimal solutions. Okay, so suppose our current BFS is xt and y is the entering variable. The change in the objective, remember, is the following. The change in the objective is going to be C transpose x t minus the objective at the new point, C transpose xt plus 1, which is equal to C transpose xt minus C transpose xt plus C transpose lambda dy, if y is our entering variable, which is equal to, the C so I just did a substitution, right? I did this substitution because this is xt plus 1. And the C transpose xt's cancel out, so it's just equal to lambda times C transpose dy, which is equal to lambda. Well, what is C transpose dy? That's the same thing as the gradient of the objective transpose dy. Remember, our linear objective function has a gradient equal to the coefficients of the cost of the objective function. So this, of course, is just equal to lambda C bar y. That's the reduced cost, remember. So we can use reduced cost to compute changes in our objective function. The step size times the reduced cost is going to be the change in the objective. I'm sorry, I should put a minus in front of this. So if this is negative, of course, we are improving in a max problem. If it's positive, then we're improving in a min problem. The signs sort of flip. Okay, they didn't sort of flip, they did flip. Okay, so suppose we have the following situation where we have a current basic feasible solution in two directions with reduced cost 0 and minus 25. And the first question is xt optimal? And the answer is, well, yes. All reduced costs are non-positive, and it's stated that this is a max problem. Okay, but are there multiple optimal solutions? The answer to this question is a little deeper than you might think. So the first, I think, intuitive response is, well, yes, C bar x1 equals 0. And that's not quite right. Or the justification isn't complete. Here's the problem. What if we have degeneracy? In other words, what if the step size is 0? So this is not right. However, we can say yes if we say C bar x1 equals 0, and we have 0, 150, 0, 200, 50, plus lambda times the direction of 1 minus 1/2, 0, minus 3/2, minus 1/2, being greater or equal to 0, 0, 0, 0, 0, leads to 3 inequalities, right? 150 minus lambda over 2 has to be greater or equal to 0. 200 minus 3 lambda over 2 has to be greater or equal to 0. And 50 minus lambda over 2 has to be greater or equal to 0, which means that lambda has to be less than or equal to 300. Lambda has to be less than or equal to 400 over 3. And lambda has to be less than or equal to 100. So all this adds up to lambda max equaling 100, right? 400 over 3 is greater than 100. So we can move in a positive way towards this, all the way to this other extreme point, which has the same objective value. And in general, what we will say is that there are infinitely more optimal solutions if we have the following two conditions. We have a zero reduced cost, and it corresponds to a simplex direction with lambda max greater than 0. Note this must mean that all other reduced costs are non-positive for max problem and non-negative